Hello and welcome. My name is Ruslan. I'm software developer at Avride, autonomous vehicle US-based startup. Here it's more like dive into the industry kind of talk, where I will share our approach for robotic 3D visualization. First, let me tell briefly about who we are. We have been creating self-driving technology since 2017. We have offices in the US, Israel, Serbia, and South Korea. Avride primal focus is on developing and operating self-driving cars and delivery robots. When you try to create better technology, it's really important to understand what happens during the ride. We have different tools for that, like metric, dashboards, but when we want to understand what really happened during a particular moment in the ride, we rely heavily on 3D visualization. A little bit of background. If you ever done robotics or had a robotic pet project, chances are that you have heard about ROS, Robotic Operating System. It's a way to organize your robot as a bunch of separated processes communicating via named channels called topics. At some point, you want to debug your robot in 3D. You care about high-level stuff, where it's located, where it's headed, why it took this turn. And you don't want to bother about low-level stuff like triangles, textures, or how it's rendered on the screen. So ROS comes with this native desktop app called RVs. It supports a bunch of primitives like cubes, spheres, lines, which you can draw in order to debug what happens with your robot. It's pretty old at this point. For example, you have to download your data beforehand, so I don't know, a couple gigabytes before you can play it. But it can be considered as a grandfather of all robotic visualizations too. Many other tools drew inspiration from it. In order to circumvent these limitations, we decided to make our own robotic visualization. Enter Avis. This is a self-driving ride through Austin, Texas downtime. Here we can see point cloud, panorama projections with 3D upon it, different trajectories, vehicles, static informations like road graph. So it's a web-based tool, so you don't have to pre-install anything. It supports cloud streaming, so you don't have to download anything. We heavily focused on read optimizations. By read, I mean latency, throughput, frame rate. By write optimizations, I mean how easy it is for our developers to add new stuff if they want to display something on the screen. Through our experience, the top priority for dev UX is how quickly you can open the ride. Ideally, it should be within the single second. So here is our read requirements. We have a huge data volume coming from our sensors. So think of HD cameras, radars, odometry sensors, lidars. For lidar, we have like 300,000 points per cloud at 10 Hz. so it's a lot of data. Also, we have a lot of developers 3D visualization. So, for example, other vehicles, trajectories, occupancy grids, static data. So, for example, on the screen, the blue and green lines are originating from other agents. Is their most likely next trajectories? The little transparent blue squares is occupancy grid, is where our car can possibly move in the near future. The transparent red one is a static road graph coming from our HD maps. And then you have other boxes, is other engines on the road. We have low latency requirements, so we should be able to open quickly, because usually you debug, you have a bunch of different events coming from different writes. So you really appreciate if you, for example, you have 20 events, if you can open them quickly. Often this event don't contain particularly what you are looking for, so you have to scan through them. And you would really appreciate if you can do this at the higher speed, ideally 2x at 8x speed. So it means high throughput. And by high performance, I primarily mean high frame rate, so 60 FPS frame rate. As we are web-based, JavaScript loops are really slow. So our solution to this, we remove JavaScript from our hot rendering path. We try to prepare the data, essentially pre-render it in advance as much as possible in our pipeline. So when the client finally receives the data, it sends it straight to GPU without looping over the primitives. So we have our own robotic pipeline, which emits the messages, which can be separated in two primal categories. One is general purpose, which requires no further pre-processing, and we save it straight away. The other one is the one that we will eventually will draw on the screen, and it requires a special pre-processing, which shows Google Flat buffers as our primary binary message format for several reasons. First of all, their read is really fast. Essentially, it's casting to a certain type, and that's it. And another feature, it has a strong byte alignment guarantees, which is required for us, so we can send the data to GPU without any further copying. So we don't need to copy it to realign it. So after that, after we receive some data, we have to, as I said, pre-render it, which is indicated by this box called shader buffer compression. We prepare, align the data, minimize its size, minimize number of its draw calls. After that, there is a general block where we ZSTD compress our data, and then we store it in our own version of Apache Arrow Parquet files, which we modified for better read performance. After that, the relevant parts of Parquet are served over the proxy. They are compressed natively by Chrome, and then they decompressed even more on the shader, and then we finally see the picture on the screen. So draw call is basically a command sent from CPU to GPU to draw something on the screen. They are quite costly because the communication between CPU and GPU is quite time consuming. That is why we want heavily to minimize them. In pseudocode, it may look like this. So essentially, we are switching from vector of structs to structs of vectors by concatenating primitive attributes. So we, like in this simplified example, we can, instead of calling, making draw call for each particular cube, we are making a single draw call for all of the cubes. And after that, we go even further. We concatenate even more geometry to a single draw call through some technique known as one-dimensional texture mask. So it's drawn in the single draw call, but at the same time, our users still can hide particular geometry through this one-dimensional texture mask. To summarize, all of those performance tricks allows us to essentially render like millions of cubes at 60 FPS on the client. So kind of the client performance is not a restriction for us because like we have plenty of that. After that, there is like a buffer size reduction step, because the less you send over the wire, the higher the compressed data, the higher throughput of your meaningful data can be. And also you can save on the cold storage size. A former colleague of ours discovered a cheap way to send integer buffers to GPU. That is why we developed this special GPU compression-decompression. So once again, on the client, we can decompress it really quickly. First of all, we center all of our attributes around primitive center, so they have more zeros in their bits, because most of the geometry is drawn within 150 meters around the car. After that, we quantize those attributes, for example, into int 16 bits or even int 8 bits. After that, many of the data becomes essentially the same. For example, it's quite often people draw something with the same color or the same size, so we can collapse it into the constant. And then the last discovery, struct of vectors leads to better ZSTD decompression, as similar things end up closer to each other. For example, all of your axes. All of those tricks combined leads to approximately 6.x smaller storage size than ROS, and it's 6.8 times smaller in the compressed space after the STD, after the compression. In the decompressed space, it's 10 to 20 times smaller, so we can save even more. For example, it's a nice bonus to save on the client RAM. After that, a little bit how we modified the storage for better performance. We took Apache Arrow Parquet data format, which is column-oriented, append-only data format, and we modified it in 3 key ways. First of all, we added ability to control the bufferization explicitly, so we can trade off latency for throughput better. The main data storage unit in Parquet is called data page. It's essentially the one thing that will be compressed by ZSTD and stored on the disk. So bigger data page means better throughput, but at some point the latency will suffer, so you have to find a sweet spot between those two. After that, we modified it so it has 8 bytes alignment guarantees, so it works nicely with flat buffers, and we have our zero copy to GPU requirements. And lastly, we add a special callback which reports to us data page size and offset, because we are creating on the fly a time-based index, so we can rewind and replay these Parquet files from arbitrary point at time. After that, the client uses this time index to request only the needed parts of Parquet, and through some clever HTTP2 headers trickery, it's decompressed natively by the Chromium ZSTD part. For example, it's much faster than Wasm ZSTD decompression. After that goes the write optimizations. By that, I mean essentially how easy it is for developers to add new stuff on the screen. Before that, our experience with visualization, it used to be something like this. When you have to add something, you have to declare in rows your visualization topic. After that, you have to drill down. It's something like signal slot based object. You have to drill it down to the place where you want to draw. So it's like 3 to 5 more invocations. Then you can finally draw on it. And after that, due to historical reasons, you have to update like 8 more places on average. It happens eventually because mostly for safety reasons, the steps was always added, but almost never removed. And after that, it was not rare to discover that you have successfully debugged your issues with this new visualization, and you don't longer need it. You can remove it, but the developers, they was willing to go through these steps to add new stuff, but they were reluctant to repeat those steps in reverse when they needed to essentially disable or remove this visualization. To summarize, the end experience looked a little bit like that. It took from 3 hours to probably 1 day to add new stuffs, because usually you go through several iterations adjusting your visualization. And through careful look, we essentially understand that primarily developers are using it for debugging, and it's more akin to printing or logging. And it gave us a clue about the desired API shape. So we designed this avride macro with essentially a printing statement, but in 3D. You have to register one and only one place to declare your topic. It's data-driven, meaning that you draw something and you instantly see it on the screen. It also has a nice property that while you're viewing, so for example, we have many teams, and on average we have 50 to 100 visualization topics, and each team needs only a small subset of them. So the end users can download only what they need. In terms of what the user can initially draw, we strived for LLVM-like approach with their separation for front-end and back-end parts. Our basic set of primitives is quite minimal, so basically spheres, lines, quads, and polygons. So we can optimize our read performance heavily, but then you can compose through these primitives your own geometry types. For example, the occupancy grid used to be just a bunch of quads, and through our read optimization, it was still efficient. This is like a picture what roughly our API set of primitives looked like, and all other things, for example, the static road graph is built upon that. Implementation-wise, we are tightly integrated with our pipeline. It works in generation, so by the end of the generation, we essentially collect the geometry drawn by user, and then we release it through some hidden implicit topic. One of our requirements that for performance and safety reasons, we have to know all of the topics in advance. That is why we created one real topic, and through it we kind of created a bunch of virtual user topics called layers, and we multiplexed. Then our data pipeline team came and said, actually, for logging performance, we have to know the number of columns in Parquet in advance too, and that is why we have to adapt once more. So essentially, we have single real topic, single real column, but within this Parquet column, we interleave data pages. So for example, we have one data page for cubes, then we have the next data page with lines. And from client perspective, it operates on the data page level, so it doesn't really care in which columns the original geometry is stored. And it's one of the reasons why we have to modify Apache Parquet so we can control data page bufferization explicitly. Thank you for your attention. We are probably have something like 5 to 10 minutes for quick Q&A session. Sure.
So this kind of login mechanism is available online now, or it's just like you talk about what you need inside your company?
So essentially the question is wherever is it open source or not?
Yes.
No, it's closed source, but actually we thought about it, and the primal obstacle is that we have a really small team, and we would need to have legal team in order to support it. But for example, if our boss asks us to open source, probably we can do it within 3 weeks, because it can be quite easily integrated with ROS too. Sure.
Was separating the positions into the X, Y, and Z meant to be an optimization in size and compression, or for rendering?
So essentially, the question it goes to this slide, and the question is: by concatenating the separate attributes, are we doing that for render performance or size performance? Great question. Actually, we are doing it for both eventually, because it gives us a render performance because we can send it in the single draw call. It comes with a cost because we are consuming something called shader attributes, and you have only 16 of them. So you can't go infinitely with that. And it's also attributes to our compression because all this centering quantization is done further, and moreover, because the similar data, for example, our Z levels, most of our geometry is planar, and our Z levels are varying within 1-2 meters mostly. So they the STD, for example, can spot the difference, there is a lot of similar data, and that is why it's compressed more easily. So to summarize the answer to your question, it's for both. Sure.
Like a general question, how can you tell how close the visualization to the real world physics? How can you?
Again, basically the question is how we can tell how close our visualization to the real world. Actually, we have the same guarantees as our pipeline. We created our own pipeline, and briefly I mentioned that it works in generations, mostly for reproducibility. Sorry, I can't pronounce it. Reproducibility. So kind of, we know for sure that our online and offline, they match closely. So kind of in visualization, we inherit the same guarantees as our pipeline. And if we are talking about desynchronization in milliseconds, we have a special calibration tool, which through random sampling, give us a fair statistical estimate of how far we are from the reality.
You write C++ and you compile it to WASM?
Sorry?
You write C++ and you compile it to WebAssembly?
Okay. I think it's about this slide. So the upper half of it, it's all done in native C++, essentially either on the car or in post-processing. And our main trick is that we are not restricted by client performance, because the JavaScript is responsible only for UI. We send all of our data straight to GPU, but GPU has special requirements, for example, OpenGL, WebGL. That is why we essentially have to pre-render all of our buffers in advance in native C++ part. And we kind of similar to video games, but in contrast to video games, 80% of our data is generated on each tick frame, so we have to load it to GPU anyway. So why don't optimize your data in such form that you don't have to loop it or iterate in JavaScript? Sorry, we are running out of time. So thank you for your attention.